It's something we totally take for granted, but every single click, every keystroke, every little thing you do on your computer is kind of like a small miracle of organization. Today, we're going to pull back that curtain and look at the hidden genius that makes it all happen, your operating system's device manager.
So think about it. You click save, you hit print, you just move your mouse across the screen. It all feels totally seamless, right? Instantaneous. But behind that one simple action, there's this absolute storm of activity, a really complex dance between your hardware and your software. So let's peel back that layer and see what's really going on in that magical split second. Just picture this for a second. You've got your keyboard, your screen, your hard drive, maybe a printer, your Wi-Fi card. They're all separate pieces of hardware, and they're all screaming for the processor's attention at the exact same time. Without some kind of conductor, it would just be noise, complete and utter chaos.
And that conductor, that traffic cop standing in the middle of this busy intersection, that's your operating system. Its device manager is the thing that steps in to create perfect, beautiful order from all of that potential chaos, directing every single request and every piece of data with amazing precision.
So, what's its job description? Well, at its core, the OS is the ultimate multitasker. It's constantly keeping tabs on every single device plugged into your computer. It has to decide, okay, who gets to use the hard drive right now and for how long? Then it has to seamlessly hand it off to the next program in line. It's a non-stop job, and honestly, without it, nothing would ever get done. But this brings up a really tricky problem. I mean, not all devices can be shared, right? You can't have two different documents printing on the same printer at the exact same time. So how does the OS actually enforce these rules? How does it manage who gets access to what?
Well, it starts by sorting devices into two main buckets. First, you've got your dedicated devices. Think of a printer. It gets locked down for one job and one job only, until it's finished. Then you've got shared devices, like your hard drive. Multiple programs can read and write data from it, and it all seems to happen at once. And this is where the OS gets really clever. It actually creates what we call virtual devices. It can take a dedicated device, like that printer, and make it act like a shared one. It uses this amazing trick called spooling. So when you and your coworker both hit print, the OS doesn't just jam everything at the printer. Instead, it quickly saves those print jobs to the hard disk, creating a nice orderly queue, and then it feeds them to the printer one by one. It's such a simple idea, but the impact is huge. It's genius.
Okay, so managing devices is one huge puzzle. But what about the actual data on those devices? Let's imagine you're trying to save a massive video file. But the free space on your hard drive looks like Swiss cheese. They're just little empty pockets scattered all over the place. How in the world does our digital librarian find a home for that one single large file?
Well, the first and most obvious method is called contiguous allocation. It's pretty simple. It just looks for one big, continuous, empty shelf to place the entire file with all its parts lined up neatly in a row. Now, this is super fast when you need to read the file back, but it's really rigid. And over time, it creates tons of little wasted gaps that are too small to be useful.
So the OS got smarter. With linked allocation, it decides, hey, let's just break the file into smaller pieces and scatter them wherever there's an open spot. The trick? Each little piece contains a pointer, like a little breadcrumb, that leads you directly to the next piece. It's like a treasure map that links the entire file together, no matter where the pieces are hidden.
And the final evolution of this idea is the most sophisticated of all: indexed allocation. Instead of a daisy chain of breadcrumbs, the OS creates one special index block. You can think of it like a card catalog for your file. This single block holds a list of the addresses of all the other scattered pieces. This lets the computer jump directly to any part of the file, instantly, without having to follow the chain.
So to just quickly sum that up, contiguous is really fast, but it's wasteful. Linked is way more flexible, but it can be slow if you need to jump around in a file. And indexed, well, it's pretty much the best of both worlds, giving you that super fast direct access, even if it is a little bit of overkill for teeny tiny files. The big takeaway here is that there's always a trade-off.
But wait a second. Before the OS can store anything at all, how does it even know which of the millions of blocks on your drive are empty? Does it have to, go and check every single one every time? Nope. It uses this beautifully simple trick called the bit vector. It's basically a map of the entire disk, represented by a long string of ones and zeros. A 0 means a block is occupied, and a 1 means it's free. So instead of physically searching the drive, the OS just glances at this tiny map and can find an empty spot in a fraction of a second. So elegant. All right, for our final act, let's look at what might be the most dramatic problem of them all. Your hard drive, the old spinning kind, has a physical head that has to move back and forth to read data. So what happens when 10 different programs all want data from 10 different places on the disk, all at once? How does the OS stop that head from just thrashing around like a maniac and slowing everything to a crawl?
Well, the most basic approach is first come, first served. You just handle the requests in the order they showed up. Sounds fair, right? Well, in practice, it's a disaster. The head just zigzags wildly all over the disk, from the inside to the outside and back again, wasting a massive amount of time just traveling between points.
And to put a hard number on it, that chaotic path resulted in 403 units of head movement. That is a lot of wasted motion. And for you, the user, that just means a lot of waiting around. There has to be a better way.
And of course there is. It's elegantly called the elevator algorithm. Instead of jumping all over the place, the OS makes the disk head behave, well, just like an elevator in a tall building. This method, often called the look algorithm, is so much smarter. It makes the head sweep smoothly in one direction, picking up all the passengers, all the data requests along its path. Only when it gets to the last request in that direction does it turn around and sweep back. No more wild zigzagging, just a calm, orderly, and efficient path.
And the result? Just look at that. The total head movement drops from a crazy 403 all the way down to 209. It's almost twice as efficient. This simple, beautiful idea is one of the biggest reasons your computer feels as fast and responsive as it does.
Ultimately, all of these clever tricks we've talked about, from the virtual devices to the file allocation methods to these amazing elevator algorithms, they all serve this one single crucial purpose: to use your hardware as efficiently as humanly possible while always keeping your data safe.
So the next time your computer takes just a fraction of a second longer than you expect, maybe don't get frustrated. Instead, try to picture that complex orchestra playing inside, the OS conducting, the librarian filing everything away, and that tiny little elevator working as fast as it possibly can, just for you. Thanks for diving into this with me.